In the article, I refer to different files and different directories. I'd like to show you what they look like on my Google Drive. First, there's the noise train directory. This is where I put the devices files that I'm using to simulate the device's voice. Next, I put this, there's a speech train directory, and this is where I put the user's voice files that I'm simulating for this program. When I run the program called Noisy Speech Synthesizer, it's a Python program, it creates 3 directories, noise training, and inside noise training, you'll find combinations of the files for the noise train at the correct length that I specified in its configuration. The clean speech training likewise contains files that are found in here, combining them into the right length for the clean speech training directory. Noisy speech training contains mixes from the noise training file and the clean speech file at different signal to noise ratios, and you'll find them here. The files that I modified in the program were the Noisy Speech Synthesizer Python file, which is found here, as well as the Noisy Speech CFG file or configuration file, which is found here. Everything up until this point in the this program on those example files has been run. M3 is the output of running the algorithm, which is, and M3 is the factor which we subtract the device's voice from the mixed voice. One key thing to speed up this algorithm is to take some spot in the middle of the 2 audio files and only submit 1 second of data to be analyzed. 1 second of data, because all the files in this program should be 16,000 samples per second. That is their sampling frequency. So that's 16,000 points. If you try to submit the whole file, which would be maybe 10 seconds or so, the algorithm would have to handle 160,000 points. So 1 second of 16,000 points is sufficient. The algorithm goes through a for loop with different m values and then collects the correlations of those values based on the algorithm in the article. And then it determines the minimum correlation. And that's the output of this program. As you can see, here's the plot of the correlation, and it takes the minimum, which is slightly above 1. So I'm going to print that. Next, I convert the audio files into text. So first I scale the files, and I have the correct text so we can compare the two. So Y6 refers to the device's voice, and Y7 refers to the mix of the user and the device's voice. DC is removing the DC component of the single. DC components of an alternating single are the high frequency components. Next, I retrieve the text results from these files. I'm also retrieving the text results from the combined files. That is the mix file minus M, which is close to 1, times the device's voice. That is what I just described as the audio combined variable. So the device's voice is here. This is what the mixed voice is when it's converted to text. You can see that's not very useful, but after the subtraction, we get the user's voice, which starts with, he was a head shorter than his companion of almost delicate. And below is this is the actual text. You see, I printed that here. So we can see that the actual text is very close to the subtracted voice. Next, we want to listen to these files for ourselves. So I'm going to create the device's voice from the array. I'm going to play a portion of it.
Yes, ma'am, it sure was. I always say you've got a wonderful husband, Miss Margaret. May I get some?
Next, I'm going to play the mix file. I'm going to play a short portion. So these are the combination of the files that the device is here, its own voice plus the user's voice.
Yes, ma'am, shorter than his companion. I always say you've got a wonderful husband, Miss Margaret.
So the challenge is to separate the user's voice from that file. And this is after the separation.
He was a head shorter than his companion, of almost delicate physique. Since then, some mysterious force has been fighting us at every...
So you can hear the user voice has a strong single to noise amplitude. You can hear the device's voice slightly in the background. Now I'm going to print the display some plots which show this. Okay. This is the waveform of the device's voice multiplied by the M factor. This is the waveform of the mixed voice, which is the combination of the device's voice and the user's voice. And it's called single 7. Here is the subtraction of the device's voice from the mixed voice, and we get this clean set, which is the user's voice. I have to emphasize, for this method to work, all files have to be in the correct phase. Finally, what I want to show you is the WER scores for our conversion. So the WER score for this conversion is 0.21. If it was a perfect conversion, the score would be 0. The reason it's not is because one word was incorrect from the true text. I hope this video helps explain the information that was presented in the article.